Hello, my name is Nathan Gray, and I am presenting on our paper, Distributed Optimization for Power Distribution Systems with Cyber-Physical Co-Simulation. In this paper, we propose a novel distributed optimization method for unbalanced power distribution networks. The method uses equivalent network approximation, which leverages the radial topology of distribution systems and results in an order of magnitude fewer communication rounds than other methods. Each microgrid controller only has access to information about its own area. Consider a two-area system with area 2 connected downstream from area 1. Area 1 will solve its local problem and then share the resulting voltage for the shared bus with area 2. Area 2 solves its local problem and shares the resulting power draw for the shared bus with area 1. On the next round, each area uses the information it receives to solve the problem again. Each microgrid controller determines if it has converged if the information it receives is unchanging. Once it is converged, the controller will dispatch the control variables to the system. We validate this method on the IEEE 123 bus system with cyber and physical layers simulated using a co-simulation platform. The co-simulation is based around the Helix CoSim platform and uses NS3 for the cyber layer, GridLabD for the physical layer, and Python for the agents. Each of the microgrid controller agents is connected via the communication network as shown in the figure on the top left and can communicate only with devices in its area, and it can communicate with neighboring controllers. In our first test, we run several cases of a 2-minute simulation with different network delays between the controllers. The optimization runs on each minute. DERs in each area provide 100% of their capacity in the first minute and 50% of their capacity in the second minute. The table shows the resulting substation power after optimization in each minute. From these results, we can conclude that the distributed method approximates the central solution, and the results are not impacted by poor communications. We can see this because by the values in the bottom row, which have delays between the microgrid controllers, these match with the values that we get when we don't have delays. And we can see that it approximates the central OPF very, very closely. In our second test, we show how the algorithm performs when conditions change quickly from minute to minute. The two figures on the right show how the distributed optimization impacts the substation power. The first with smoothly changing generation and the second with rapidly changing generation. The black line is the power with no OPF, and the blue line is the distributed OPF, and the red triangle show the central solutions. In both cases, the distributed optimization method works equally well. This is because the optimization restarts at the beginning of each minute and does not consider data from past solutions. In conclusion, we have presented a novel distributed OPF for distribution systems that is fast and resilient to poor network conditions. We used a cyber-physical co-simulation platform to simulate the algorithm in action. The cyber-physical co-simulation allows for us to see how algorithms work with a realistic communication system with all the complexities included. Because it is also a multi-agent system, agents run separately in parallel as they would in reality, and can only share data via proper channels. We are already in the process of implementing other solvers, and in the future, the CoSim platform can be used to benchmark other algorithms, and it can also be used with other communication strategies and protocols.